Can everyone see my presentation?
Yeah.
Yeah. Okay. Ryan, let me know when you're back and I'll get cracking. Okay, right. So first thing I've got for you is the best video I could find anywhere on what MSA actually is and means. Okay. It is really simplified, which I really like about it. So it's the first thing we're going to play, then we're going to go into a discussion, and then I have been away with a couple of my learners from my first cohort, and we have created our own little case study on MSA so that you can see a really simple basic gauge R&R MSA being run. Okay, so I'm going to play the video. Normally it plays on everybody's screens. If for some reason it doesn't automatically play on your screen, then just hit the red button in the middle and it should play. If I get any reverb, I may mute you just because everyone else can hear through the speakers. Also, sorry, just to pause there for a second. It's a really good free white belt certification course. So if you haven't had the opportunity to do something like that before, I do recommend, and if you've got a couple of hours, that you give it a try. It's a really good course. You can also put it on your off-the-job training log if you want to. Okay, cool. So I really think that introduction video simplifies what an MSA actually is. So I have got 5 questions and 5 people, which is lovely. So you can all have 1 question each. So I'm going to start with Pete. You can take what is a measurement system analysis. Michael, I want you to take why do we use MSA? Terry, I want you to have a look at what do I mean by a confidence interval in relation to MSA. James, I want you to take what does rule of tens mean in relation to MSA? And Ryan, I want you to take what could cause errors in our measurement systems. I'm going to give you all 5 minutes. I want you can use Google, have a research if it's not something you already know the answer to. And then once we've all responded back, I'll go through and I'll summarize all of that for you. Everyone okay with that? Me thumbs up? Yeah? Cool? Excellent. Sorry, you can probably hear Peter in the background there. Okay, how are we doing? Everyone ready?
Born ready.
So
Born ready. Okay, Peter. So you got question number 1. What is a measurement system analysis?
A measurement system analysis, or MSA, if you will, is a thorough assessment of a measurement process, and it generally includes usually a specifically designed experiment that seeks to identify the components of variation in that measurement process. So just as the processes that make a product may vary, the processes of obtaining measurements also vary. So the measurement system analysis evaluates the test method, measuring instruments, and the entire process of obtaining measurements to ensure the integrity of data used for analysis and to understand the implications of measurement error for decisions made about a product or process.
Okay, fantastic. So I think that in itself shows us why 85 to 90% of people think the measurement system analysis is really scary and really, really difficult. So, you know, it does get presented out there with a lot of very technical terminology when it comes out. So I'm going to simplify that in a minute for you, but everything Peter said there is 100% correct. I think that is kind of the very high level way in which to describe that. So, okay, Michael, why would we use an MSA? Oh, that's okay. Putting notes in the chat. So it is to help assure that data being collected is accurate and systems of collecting the data is appropriate to the process. Good, reliable data can prevent wasted time, labour and scrap in a manufacturing process. 100%. Yeah, completely agree with all of that. That's brilliant. So, Terry, what do we mean by a confidence interval in relation to MSA?
Well, I thought I knew what it was, so I didn't Google it. And then at the last minute, I was like, is it that? So then I Googled it and Google disagrees, so now I don't know.
Oh, no, you just confused yourself.
I thought that it was the range in between the lower and upper limit or number.
No, that's your upper and lower specifications. That's your tolerance within your MSA.
So then
within an MSA, you set that lower limit and you say, okay, so my screws at a minimum need to be this, and at a maximum they can be this, and that's the tolerance that you're looking for within
so
your
then when
measurements.
I Googled it, it said something about mean, but then it totally confused me.
Okay, cool. No worries. We will go through it in 2 seconds. So, Ryan, rule of tens. What's a rule of 10 within MSA?
Oh, I had that one. Yeah, I didn't get that one. Yeah.
No? Okay, cool. No worries.
Beth, you said for that one for me, didn't you?
Oh, did I? Sorry, James. Did
Yeah.
I jump in a row there? That was my fault. Apologies. It's because I didn't do it in order of people on the screen, you see. I messed myself up there. Go on then, James. What does rule of tens mean?
It says that the resolution of your measurement system should fit at least 10 times into the process variation that you're measuring.
Yeah. 100%.
And then there was another thing, like the bucket rule, adhered to a 10 bucket rule. If that's the same thing, that you divide it by 10 and then record the data to the nearest thousandth.
Yeah, very much so. You know, but what they're saying, you know, simply is don't have too much data. You don't need to measure it 73 times, because measuring it 73 times is going to completely confuse your measurement system. So rule of 10 is stick to groups of 10 with what you're doing. Sorry, Ryan, I'll now ask you the right question, just to totally not throw you there completely. So what could cause error within a measurement system?
Cause errors, operator taking the measurements, the equipment, the environment, and the process of measuring.
Yep. Fab. That's brilliant. Okay, so I'm just going to do a summary for you now, just really simplified summary of those questions. So a measurement system analysis is used to identify and analyze the accuracy and precision of a measurement system. Okay, it's not of the screw, it's of the system that you're using to measure that screw. Okay, and it's to validate the measurement system and confirm that your data is reliable so that you can make decisions based on trusted and reliable data. And if you look at Six Sigma, which is why I recommended in the last one that you do go and have a look at that white belt. So just a short online course. It's really good because if you look at Six Sigma, it is the measure phase. You have to do it. It is mandatory. And that is why they've made it a mandatory part of your projects at the end. So whichever project you decide to do, you are going to have to deliver an MSA within that project. And today we're going to very specifically look at gauge R&R MSAs. So if we have a look at a confidence interval, a confidence interval is the range of values of where we're fairly sure our true value lies. So if we're saying that we are 95% sure that our values will sit within those ranges. So 95 times out of 100, when we measure, it is going to come between our lower and our upper specification limit. So it's not the tolerance between the two, it's our confidence in how well our measurement system is going to work. And we always give that confidence about 95%. If you give it 100%, you've screwed yourself at the beginning. Okay, you're going to find that really difficult to achieve. So you always want to give yourself at least 5% within your confidence to allow for things to fall outside of the measurement system, because nothing is ever 100%, especially when you have a human involved in that process. Okay, because we are all different and we do things differently. Okay. So if we have a look at rule of 10, the technical definition is the units in your measurement system must be able to fit into your specification width 10 times. You should be able to divide your unit of measurement into 10 parts or more. So when we look at a gauge R&R, okay, we look at that we will measure 10 parts, okay? That each operator will measure those 10 parts 3 times. So you will then have 3 operators measuring those parts separately. So in total, you need 90 to be able to run it, okay? So each operator is measuring 10 parts 3 times, and you must have a minimum of 3 operators within your gauge R&R, okay? Because otherwise, how do you see what the difference might be? Because really, and as Ryan said earlier, the biggest issue we have with measurement system analysis is the operator. It's the human being who is either operating the measuring equipment or completing the task, because everybody does everything slightly differently. No matter how much we follow a process and we try to standardize what we do, the human error is always the biggest value that we will have. As Ryan said earlier, the other things that will affect that is environment, your equipment. It could be damaged, faulty, lack of calibration, ineffective process or method, and the material that you are using to do it. The other thing that could affect measurement system analysis, and as I was quite specific about it, is having a wrong sample size, having too much or too little data. Okay, it skews it. What you want is a snapshot. It's not meant to be that every single time you measure every single part, you run a measurement system analysis based on that. It's not meant to be that. It's meant to be a snapshot of a process that you carry out to measure those particular items to see that your measurement system is working. Okay, so keep into that, and I'm going to give you a template that allows you to do it that way after the session. So I'm now going to show you a little MSA case study. So the scope of our case study today is Weasley Screws produce decking installation products. They have won a national contract with a national decking company, retailer and installer called eDeck to provide their decking screws. The retailer requires the decking screws to be between 63 millimeters and 63.5 millimeters. Now, one thing, because I just out of experience from doing these case studies and, you know, working out the best way to present the data, etc., can tell you the bigger the gap between your lower and higher tolerance limit, okay, the more skewed your data will become. So you need to keep that tolerance quite low. And sometimes, you know, especially if you work somewhere where you've got manufacturing and parts that you can measure, etc., your tolerance limit would naturally be quite small. But keeping it to, you know, 0.5 centimetre or, you know, 1 centimetre at maximum is kind of what we're looking for. So I'm going to show you a 48-second video, okay? This is me, as you can probably tell, and some of my other learners as 3 separate operators doing a measurement system analysis that we have been asked to complete. I really want you to watch the video because the video reflects the outcome at the end. So I want you to note down the things you can see in the video that you think that we're not doing or we are doing really well within that, because it is then going to affect the result that we get at the other end. It's got some funky music as well, guys, because you can tell that I shot this video and then put the music on the background. So I hope you all appreciate my funky music. Okay, short and sweet. It was actually like about 15 minutes long, but as you can see, I really sped that up so you didn't have to sit there for 15 minutes watching us measure some screws. But take on board what you just saw there, what you saw us doing, where we were, what we used to do those measurements. So, looking at a gauge R&R. So overall, okay, what we want to look at in a gauge R&R is our tolerance limit, okay? So as you can see, this lovely little table here shows us what's good and what's bad. So an acceptable tolerance limit on a gauge R&R is between 0 and 10%, okay? If your tolerance limit sits between 10 and 30%, then it may be acceptable, okay? But there are some things that you're going to need to improve because it isn't that accurate in what it's doing. If it sits over 30% and anywhere between 30 and 100, it's not an acceptable measurement system. It's not working. Yeah. So those are the main overalls that we're looking for within that. So mainly we want to see what is our tolerance. So I'm now just going to stop sharing my screen for 1 second. I'm going to bring up a different, oh, not my diary, because I'm sure you don't want to see that. So there we go. So as you saw in the video, this is what we were recording the data. So you can see there's operator A here. Yeah. So operator A went round and measured part 1 3 times, part 2 3 times, part 3 3 times, all the way. Then we've got our operator B, and then we've got our operator C. Now, our gauge R&R template, which is the R&R template that will be provided for everybody. Okay, as you can see, it's not the way that the data is laid out. Yeah, so having it in a giant long list like this really doesn't help you when you get to the point of having to transfer that data into your gauge R&R template. So please check one I did earlier. I've taken those measurements and laid them out as they would sit. So I've put the parts across the top. Each operator's got their own table and their 1, 2, 3 readings for each part. So I'm going to take this detail and I'm going to start transferring it over to my gauge R&R spreadsheet. Okay. And I have to take each operator separately, because we have to remember this is a macro enabled spreadsheet. So therefore we do not want to be deleting any of the actual template, because then that will skew our results. And then the next thing we need to do is we need to give it a name. So we're going to call this Weasley's Screws. The date of our study, I'm going to pretend that I definitely recorded that video this morning. It was performed by myself. Okay. And then I've got my upper and lower tolerance limit. Okay. So my lower limit was 63.
63.
My upper limit was 63.5. Okay. So I've put in my data at the top. Now, a standard deviation multiplier is always 6. It's a 6 sigma thing. Please don't ask me why it's always 6. It just is. Unless somebody tells you to change that figure, do not change it. It's how the spreadsheet calculates everything. And then we scroll down to the bottom. And as we can see, this table here has now populated itself, hasn't it? So what's the first thing you can see, guys, that you can tell me on that?
There's no variation on appraiser.
So nope, there is no variation on the appraiser. What about that?
Is this because, oh, I don't want to say it wrong now. Is this because the measurements weren't taken randomly in order? They were done in order.
Yes. Exactly that. So what you saw was that we, as in that video, sat next to each other, didn't we? That was error number 1. That was error number 1. Okay, was that we were sat together. We should never have been sat together to measure the same 10 parts. Okay. Not only that, but did you notice the way we were putting them on the table?
Straight in order.
In order, and then I passed that over to the next person, and the next person then took them and put them back in order. So actually it can't calculate that, because how do we know that it was part 1 that was measured in each of those boxes? We don't, do we? Because of the way the screws were measured and they weren't being controlled at that point. So it won't bring you out that variation. What else on the top one can we see on our overall tolerance here? What's our figure? And what did our chart say a minute ago was a good measurement system?
So between 0 and 10.
Yeah. So what's that tolerance on there?
39%.
So what does that make it?
It's a bad R&R.
It's a bad R&R, isn't it?
Yeah.
So then we can see here, it's looking at our reproducibility and our repeatability. Okay. So we now have tolerances for those as well. So we've got reproducibility. So what is reproducibility, guys?
The same people, same tool, same people. No, same people, same tool, different people.
Yes. Yeah. So our reproducibility is 23.98% tolerance. So what does that tell you?
That it was okay. Well,
yeah,
borderline.
Borderline. It's okay. It's not great. Do you know what I mean? It clearly needs improvement, but it's not bad. What about repeatability?
So it's the same person, different equipment.
No. Nope.
It's the same.
Same person, same equipment. So it's now looking at, rather than looking at all 3 operators, it's looking at each one separately. So how repeatable is it for this guy to repeat that 3 times?
This is why when they haven't done it in random, it's flagged in like a problem.
Yeah.
Because the more that you use a tool, the more that you get used to the process.
Yeah. And actually, one of the other big things is, did you see the way we wrote it down?
Yeah.
So they could see what I wrote.
Yeah.
So therefore, it gives you bias, doesn't it?
Yeah.
It makes it bias because you're going to look at it and look at part number 10.
Yeah, you're never going to think, oh, I've got 65, but they got 63, so I'll still write my answer.
And how rare is it that you're going to get 3 parts measured by 1 part measured by 3 people 3 times, all exactly the same result? But by the time you got to here, do you think people are copying each other's results?
Because they can't be bothered.
Well, no, so I don't think it's even that. It's because if it's different, then they think, well, why is mine different? If everyone else has said it's 63.1, why would mine be 63.2? You get it again with part 8, where they're the same across the board. And actually, you can see the most variation comes from number 1, because the first person that measured them couldn't see. And if you look at parts 2 and part 3, sorry, operator 2 and operator 3, very similar results, aren't they, across the board? So that's why you get quite a good reproducibility, but not a good repeatability. Is that making sense to people?
Yeah.
So the other lovely little thing you get with this template is it actually gives you the information at the bottom of it as well. Okay. And it'll tell you what your, good measurement system, bad measurement system. There are a million things that you could go into with MSA, but what you need to know is, where is your tolerance? Yeah. Is it repeatable? Is it reproducible? If that sits at above 20%, it isn't a good measurement system that you have used, okay? And you need to improve it, and that data is not reliable. Okay, so this template was attached to the Talent LMS, but unfortunately, when it's been uploaded, it's changed the file type to make it a XLSL file, and therefore the macros and the things don't work in it. So your tutors all have copies of this that they can hand out to you for your endpoint assessment projects, or for your Unit 7 if you are still to do anything on Unit 7. But basically what you are looking for is this overall figure here. What is the tolerance of your reproducibility and your repeatability? Okay, and really you want that to be lower than 10%. It's lower than 10%, then your measurement system's fantastic. So what did everyone think about that? Does it make sense?
Yeah.
Kind of. Yeah, I think.
Yeah. What's not making sense
whether
to
we
you,
need to do
Ryan?
like an example of something like that. I know you've gone through an example, but physically doing it.
Yeah, and that's what I found with it, is that physically doing it makes your brain take it in. So what I would advise you do is take something that you have 10 of, yeah, take it round to 3 different people using the same tool, and ask each person to measure it, each one of those 10 things 3 times, but don't tell them the order in which you give it to them. So color code the parts for you. Yeah. So you could do, one's red, one's yellow, one's green, one's blue, one's purple, one's pink. You know what I mean? They don't need it in the same order, as long as when they hand it back to you and tell you what the measurement is, you know that's part 10. Then you write down the measurement in part 10. But the more anonymizing you make it, if that's the right word, if that's even a word, I'm going to go with it is anonymizing that you make it, the better. Yeah. So they don't want to see each other do it. Don't let them see each other's measurements. Don't let them do it in front of one another. Randomize the order in which you give them the parts each time, but have it coded in some way so that you know where to put down the results, and then enter the data into your Gauge R&R spreadsheet. And it will tell you whether or not that measurement system was any good. And that's the simple thing about it, is once you've got this template, it just tells you. You don't need to analyze the data. All you need to do is take the measurements, and the spreadsheet will tell you whether it's any good. And then you can look at, okay, so that's come out at 39.18%. What's wrong with my system? Yeah. And if we all look at what was wrong with that video, We can easily walk through it, can't we? 1, the operators measured them together. 2, they didn't measure them in a randomized order. 3, they did it with a ruler. Not the most precise of measuring things, is it, a ruler? You would more expect it to be a calibrated measuring device that they use to measure it. Yeah? So, you know, you've got 3 things immediately there that if we had done it separately, using a calibrated device without being able to see each other's results in a randomized order, we'd have probably come out with a very different result to that measurement system. So definitely go and give it a practice, because you're going to have to do it for your endpoint assessment project. This video will be available at all times. If you are in any way, any of you in any way struggling with it, then bring me data and we'll do one together. It won't take 15, 20 minutes. We can go online, we can bring the spreadsheet up, we can put the data in, you know, but the best thing you can do is go out there and give it a try for yourself so that you physically do the action of it. Okay, and there are many other types, you know, there's binary MSAs, there's ordinal MSAs. If for your endpoint assessment project, you need to do something that is above a gauge R&R, then do come back to me and let me know. I can provide additional training on the other types of MSA out there if needed as well. But what I just wanted to do today was demystify the process a little bit and, you know what I mean, show you that actually if you are measuring something, it's quite a simple process. The most difficult part is labeling up the thing that you're going to measure and then making sure you give it out in a randomized order and use the right measuring equipment.
Cool.
Cool. Everybody happy with that?
Yeah.
Yeah. So the video will be available. Terry will send you all over a copy of the spreadsheet from today. We can't upload it onto Talent because it takes away all the macro enabled, which breaks the whole spreadsheet.
My computer's not allowing me to download that spreadsheet with macro. That's why I keep having issues.
Really? Why? What's it saying?
It's saying, because that's why I keep flagging it up. It's saying Microsoft has blocked macros from running because the source of this file is untrusted. I've clicked on learn more and it says it's blocked on my computer.
Oh, you need to speak to Pete about that. It's not a dangerous file, so it shouldn't be blocked. I don't know why your admin is doing that.
I've used it before and all of a sudden.
That's just a settings change. It won't take me long once I get on your machine.
Okay, thank you.
Cool. Yeah, speak to Pete, get him to remote in and change that. If it does that with anybody else, definitely speak to your IT because it is just macro enabled. It's a blank spreadsheet when you guys get it. Okay, it's just a blank template. It's just a 1 page, and then you create your own data into it.
Yeah, perfect.
Cool. Well, I hope that was all right for everybody.
Thanks,
and that I didn't break your minds with MSA today and actually made it sound a little bit simpler than the 4-hour lecture that to me made it sound really super complicated. So I hope that was helpful. Anybody has any questions after the session, just give me a shout.
Thank you.
Cool.
Thank you so much.
Thanks, guys.
Pleasure. Nice to see you guys.
See you later. Cheers.
Bye.
Bye.